Today I want to introduce System F to you, which is essentially a polymorphic lambda calculus. And we will also play with some type system extensions around records and variants. In this manner, we will also run into type equivalence and structural subtyping. Obviously, assume that prior to this lecture, you have acquired knowledge in the basic lambda calculus, the untyped version, and the simply typed one. Okay, so let's just introduce System F by comparing it with the untyped lambda calculus. So we see two functions here, the ID function, identity, and the twice function, which applies a given function f twice. And then down here we see how we get a typed version thereof in System F. So we have additional type abstraction going on. In this manner, we make this function polymorphic. So we basically have a uppercase lambda, a big lambda, and the big X is basically a type variable. So this is how we parameterize identity function in a type. And then we also use the type variable uppercase X to indeed declare the type of the lambda variable X here. Okay, and twice, well, it's also parameterized by a type variable, and then the function argument here has the appropriate function type, it's polymorphic, and the argument X, lowercase x, is of the type uppercase X, and then we just continue as in the untyped setting. Okay, so in this manner we see that System F basically introduces polymorphism. So let's play a little bit with these terms, with ID and twice. And in this manner we actually see some additional expressiveness. Okay, so let's look at some expressions and their types. So ID, the ID function, is of course of a polymorphic type, and this is pointed out by the for all x here. So in a way, we essentially bind type variables, and then argument and result type are the same, x. Now, an additional bit of expressiveness enters the spot here. So we also have what we call type application. That is, we can actually apply some given function to a type. And we have to do this whenever we actually have a type abstraction in front. And remember, the ID function in System F starts with a big lambda to receive a type X. So what we do here is we indeed apply the ID function to some specific type, let's say bool type. And in this manner, we essentially specialize the ID function. It's now no longer of this polymorphic type as in the first line, but it's now of type bool type to bool type. We can go on and now actually perform regular function application. That is, we apply the type instantiated ID function to true, well, and the result of that application would be bool type, of course. If we just went ahead and we would apply the ID function right away to true without this extra type application, in System F, this would be a type error because we first really have to resolve the type because the type abstraction is in front of the regular lambda abstraction. Okay, so here's the type of the twice function. It's also polymorphic type. So it takes a polymorphic function from x to x, it takes an x and returns an x. And again, we can specialize it here, we can specialize it for not type, and then we can also pass in the successor function here. Okay? So it's actually interesting to see how System F comes along in a language like Haskell. I will be pretty superficial here, but just to give you an idea, I mean, Haskell, of course, supports polymorphic functions. It essentially supports some variation on System F, but it also provides some conveniences, as we see here. So obviously we can declare the ID in the twice function in Haskell, and as you know, Haskell provides type inference, so we don't explicitly need to attach the types here, but nevertheless, these functions are still typed, and they're also polymorphic, which we see here. We look at the type of ID, look at the type of twice, and well, we don't use uppercase letters here for type variables, rather we use lowercase IDs here. And more importantly, you don't see any for all here, so it's just ID, type variable T to type variable T. So in a sense, these for alls are implicit. In fact, in the appropriate version of Haskell, you can also use explicit for alls, and eventually when you want to write certain kinds of polymorphic functions, you actually have to use explicit for alls, but we kind of skip over this somewhat more advanced topic here. You might also look it up by the name of rank n polymorphism, higher ranked polymorphism. Okay, and as you see here, not just can we leave out the for alls, and also we leave out the type abstractions here. Accordingly, we also can leave out the type applications. Okay. So now here are the straightforward rules for the reduction semantics of System F. There's a lot of similarity with the basic lambda calculus. So here we just simplify the function position of a function application. Once the function position is a value, for example, typically a lambda abstraction, then we go and simplify the argument position of the function application. Once both positions are in value form, we can actually perform the better reduction. That is, we can substitute the argument within the body of the function. So this is just normal lambda calculus. And now down here, the remaining rules deal with the new expressiveness for type abstraction and type application. There are two rules for type application. One is about simplifying the expression to which we want to apply a type, pretty much in the same way as we also simplified here the operands of function application. Okay, and once the first position of the type application is in value form, and here it needs to be a big lambda rather than a small lambda because we want to apply type. Well, yes, then we just perform substitution in a way similar to what we have seen also for regular lambdas, right? So we basically replace the type variable x bound by this lambda here within e by t. And here the last two rules just remind us that we have two value forms now. I mean, as previously, of course, we have the value form for small lambdas, and now big lambdas also provide a value form. Okay, so let's look at the type system for System F. Obviously, there are a few rules that are similar to the simply typed lambda calculus, and then there are specifically rules dealing with the new expressiveness of System F. So the first rule here, this is pretty much like in a simply typed lambda calculus. So when we hit some variable x, well, x is of the type whatever the context gamma says. Okay. When we look at the type of a lambda abstraction, it's obviously of a function type, and the argument type should be the same type as we declare for the lambda variable x here. And the result type, t2, should be the type that we can determined for the body of the function while we adjust the context appropriately so that we keep track of the fact that within the body, E, the variable x is of appropriate type T1. Okay, and then here we also have the typing rule for function application. Essentially, first operand needs to be of a function type, second operand needs to be of the argument type of the first operand's function type. That's all as before. And now here we have type abstraction. So type abstraction basically means that we have an expression of some polymorphic type. And we also use the context here now to record the fact that we are binding the big X here, right? So within the enriched context, including now an additional type variable X, whatever the type of E is, kind of the polymorphic version thereof with the explicit for all, that's the type of the type abstraction. And then when we have type application, well, obviously in order to be able to apply a type, we need a polymorphic type for E, okay? And then we just applied T1 indeed for the type variable of the polymorphic type within the body of this polymorphic type. So this is again also very similar to beta reduction. No surprise. Okay, so I guess it's pretty obvious that we can do things that we could not do previously in the simply typed lambda calculus. So for example, in the simply typed lambda calculus, we could not even give a type to the identity function. I mean, no useful type. We could only kind of instantiate the identity function to whatever specific types we had around, such as natural numbers or booleans. So obviously we can, as we were showing earlier, we can assign polymorphic types to functions like identity and twice and so on. But in particular, the ability to have for alls, so to have explicit binding mechanism here for type variables, that really adds some strong expressiveness. So one way of showing this would be to define a fixed point combinator, a typed fixed point combinator within an appropriate variation of System F. And actually, a simpler demonstration of the expressiveness here is to assign a type to self-application. So what is self-application? Look at the untyped version. Self-application basically means given some x, we apply x to x. And I mean, in itself, this is not terribly useful, maybe, but just to give you some intuition, self-application is close to the kind of cloning, copying that you would need if you were, for example, defining a fixed point combinator. So anyways, trying to do this in the simply typed lambda calculus, we realized that this is impossible. I mean, it's not even possible for any specific instance, like even if you were okay just to deal with natural numbers or anything, it's just fundamentally impossible. Why is that? Because whatever type we would need to declare for x here, that type would need to be both a function type and its own argument type. And if you think of this, this is just freaking impossible. So there's no way that we can actually get a type version of self-application in anything close to simply typed lambda calculus. However, in System F, and here we really rely on the fact that we have type abstraction and that we have polymorphic types with for-alls, we can actually define a self-application. So you might need some extra time to go through this. But let me just give you the gist of it. Okay, so just compare the System F version with the one in the untyped lambda calculus, and just ignore all the type information here for a second. Then you see it's the same term. It's lambda x dot x applied to x. So it's the same term, but we declare the type of x, and there's an additional type application going on. That's the only difference with the untyped lambda calculus. Now, what is the type of x? It's a polymorphic function type. And now here, in x, we instantiate x to a polymorphic function type. So we essentially go from a simple polymorphic function type to a type where the argument and the result type are now again a polymorphic function type. And because of that, x having a polymorphic function type, we can apply x to that x. And again, you probably just need to play with the typing rules of System F on paper to see that this all works out. But it's a cool sign of expressiveness. Now let's go on and add some extensions to System F. And there's many things we could do, and I will only pick out some examples here. In particular, I will play with records and variants, because this brings us closer to what we are used to in actual programming languages. For example, in Haskell, we're used to algebraic data types, or in some other languages, we might use records, or eventually we might also think about classes. And so this brings us a little bit closer to that sort of expressiveness. So here we imagine a type of shapes, and this is how we declare record types, and it has a component width and a component height, both of float type. And so this is a record type here. And now we combine the record type for rectangles with another record type for circles. In fact, the rectangle column and the circle column, this is part of how we combine the record types. So it's basically a tagged union. So we say we have either this record or that record, and we distinguish them through rectangle versus circle tags. Okay? And now we can define, for example, a lambda that takes a shape. So here, indeed, we take an S, and it's exactly of the type that we had seen here. And here we now engage in what you would call case discrimination. So we perform a case discrimination on all the conceivable variants. So it can be either a rectangle or a circle. And then these cases succeed if S is of the appropriate variant. And then in the rest of this case here, we receive the value from the variant. And in this case, of course, it's of the record type for rectangles, whereas here it's of the record type for circles. And as you see, eventually we just end up performing projection, or sometimes we call it selection, on this record here to access width and height. So we compute the circumference of a rectangle or a circle here. Okay? Yeah, so this shows us all the expressiveness that we have with records and variants. So we can express record types in these braces here, pointing out the component names and the component types. We can form variants with this OR, and each variant has a name. And then we can select components from records. We can perform case discrimination on variants. Well, just a quick look at the semantics. I only show the semantics for records here, not for variants. So this is actually how we construct a record, just by putting appropriate selectors in front of some values. Okay, this is just the obvious thing that we can form a record by putting braces around it and pairing up values with selectors. This is how we perform projection or selection. Well, here we just prepare projection and selection by first getting the expression into value form. And once we are in value form, we just take this selector here and pick out the appropriate value. And of course, a record where all the components are in value form, that's also a new value form. Okay, so this semantics is pretty straightforward. And here are the typing rules for records. Well, once we have a record expression where all the components E, I have these appropriate types ti, well then this record expression is of a record type. That's really obvious. Or here, if we have an expression E of a record type and a selector that also shows up in this record type, well then we go on with the appropriate component type. Nothing surprising really at all. Something a little bit more interesting. We should probably expect some sort of type equivalence for record types. Let's look at examples here. We should probably not bother much about order, right? So the components in a record are labeled anyway by a selector, and these selectors of course should be pairwise distinct. So we shouldn't bother about the order of components otherwise. So this is pointed out here with this example. And we just basically show a bunch of combinations of types, whether they are equivalent or not. And obviously, for example, in the most simple case, float type and bool type are not equivalent. Or here, when the two types are in a different order, so here it's first x and then y, and here it's first y and then x, well, nevertheless, these record types are equivalent. But of course, once we start to mess with the component types, this is no longer true. How do we plug that sort of type equivalence into the type system? Well, one very simple trick, it's not necessarily very algorithmic to do it like this, is to have an extra rule like this. So we basically say E is of type T if E is of some type T prime, as long as these two types T and T prime are equivalent. And now we would need to define rules to define actually what we mean by type equivalence. In particular, we would like to cover these cases here. And I think you can imagine how this goes, so I skip over it here. So here's a somewhat more interesting problem, structural subtyping. So think about subtyping as in the OO language, for example, where you have something like interface polymorphism or subtyping based on subclassing. So we want to do something similar here. So subtyping should be such that if we have a function that expects this sort of supertype here, and now we say that this is a subtype thereof, then this function should also be able to deal with a value of the subtype. Let's first understand how these two types differ. So the subtype seems to lack the variant for circle. The subtype also, as far as the rectangle record is concerned, has an additional component filled. Why would a function that expects a value of the supertype also work with a value of the subtype? The intuition is very simple. According to the subtype, circle is no longer an option. But if the function is able to deal with a circle, but there's not going to be any circle, that's not a problem. So yes, the function could also take a value of this subtype. Likewise, the subtype has an additional component filled, and the function, though, doesn't know anything about this additional component because its contract is based on the supertype without filled. So the fact that the function may receive something that has an additional component is not at all a problem. As long as all the components are still there that it assumes are there, everything is fine. Okay, so this is quite cool. So we now have a notion of subtyping for records and variants. And so how do we plug this subtyping into the type system? And of course, we still need to figure out how exactly these subtyping rules come along. But we assume a subtyping relationship here, just kind of generalizing the type equivalence that we assumed earlier. And we can plug subtyping into the rule for function application, because this is how I just motivated subtyping, right? A function can take a value of a subtype compared to what the function has been declared for in terms of the argument type being a supertype. So just to remind you, this is the function application reduction rule without subtyping, right? So E1 is of a function type, E2 is an appropriate argument type. Now here, E1 is still of a function type, E2 is of some type T1 prime, and it doesn't need to be the same as T1. It doesn't need to be the same as the argument type of the function. It only needs to be a subtype of that argument type. And of course, we have also reflexive situation here, so it can also be the same. Okay. Now, here are the subtyping rules for records. So, and again, I only show the rules complete enough for records. There's no rules here for variants. And also, I assume that some of these bits are a little bit tricky, so you probably again need to play with them yourself. In particular, the subtype rule for function types is amazingly clever. But I just run you through these rules very quickly, and then please take your time to look at them closely. So the first rule is very simple. It just says, well, subtyping also covers type equivalence. So this means subtyping is reflexive. Then the second rule basically makes things transitive. And the third rule essentially says, okay, if you have more components on the left, on the subtype position, than on the right, then this is a subtype. Yeah, and remember, we had this additional component filled, and indeed, that was a subtype. Now, we also have something clever here with regard to the component types. So this is also what people sometimes call deep subtyping. So we generalize subtyping beyond just adding components. We also say, well, even when they have the same components in terms of the selectors, we can have some components, let's say, for example, TI, where the subtype component is of a subtype of the supertype component. And remember, because we have transitivity, this means we can do this for any number of components, of course. And generally, we can combine all these forms of subtyping, if you like. So this means subtyping for records, it's not just that we may have more components, it may also be that some component types are specifically in subtyping relationship. Okay, this is I think still pretty understandable, and here's now a little bit tricky part. So obviously we somehow need to define how function types are related in terms of subtyping. Just look closely at the indices here, and so you see that the subtyping relation is essentially flipped for the argument, so the prime is here, whereas it's kind of in the same order for the result type when compared to the function type. So we also call this covariance, because same kind of order in for the result, and contravariant, sort of different order, if you like, for the argument. And to understand that this is the type-safe choice, and that this also can be used to some extent, we can easily fill up a lecture on covariance, contravariance, invariance. Not going to do this here, but there's of course more details in the book. Maybe one final word on comparing the kind of records that we just discussed, or records and variants, with the type system in Haskell. Well, we do have records in Haskell, so we can define such a type shape here, and there's one constructor rectangle, another constructor circle, and we have all these components that we have seen previously. There's a quite fundamental difference between what we have here versus what we had added to System F. So first of all, what we have here, this is really an algebraic data type, and the fact that this looks like a record type, or we call it record type, well, this is merely syntactic sugar for the constructors of the algebraic data type. And also because it is an algebraic data type, it's a new type, so we have a nominal type here. So this is not just defining type structure, we really have a new type here, shape. So there would be also no way here with this sort of syntax, let's say, to define subtyping for such types. So we are, in a sense, we're a limit here. Well, the good news is, if we don't use exactly this syntax, but we do some clever tricks with, let's say, type classes, we can actually encode extensible records, or if you like, also variants in Haskell. And there's a nice paper from many years ago where we discussed this in detail. Okay, so this is probably enough on this topic. So I introduced the polymorphic lambda calculus System F, and also added some type extensions for records and variants. And we discussed a little bit structural type equivalence and structural subtyping, and hinted a little bit at nominal subtyping. Thanks.